Okay, so we're going to tackle our first vector field with three variables and three components. So we have here the vector field f of x, y, z, and its first component that we see here, that component is the component m. And if you write out the function notation of x, y, and z possible variables that could be there, and the second component here, that's the component n still. I'm not going to write the parentheses x, y, z, but it's there. And then the third component, x squared cosine z plus y, that component is called p of x, y, z. So when we check for conservative vector field before, what we were doing was, the fancier term was the mixed partial derivatives being equal. So remember, if this vector field is conservative, this first term that we see here was the x partial derivative, and this is the y partial derivative, and this is the z partial derivative. We need to check to see if these different pairs of mixed partials are equal. So we need to check to see, and I'm going to expand it a little bit more here, and then we'll come back and see the vector field in a moment. So we're trying to find out, like we did before, if we do the first component's y partial derivative, will that be equal to the second component's x partial derivative? But now we have to expand that and see, well, does the first component and the last component, p, match up? And you do their mixed partials. So you do m with respect to z and p with respect to x, because those are the mixed match terms. And then you're still not done. You still have to check to see, does the middle term match the last term if we do their opposite derivatives? So n with respect to z and p with respect to y. And all of that is what we have to verify to see, is this a conservative vector field? Takes a little bit of effort to get that to work out. Later in the chapter, you're going to find out that there's another way of looking at this test that's related to some other vector operations, but for right now, this is the way to write it, and it's the way we're going to process it. And so we need to determine, well, what is the y partial derivative of the first term? You know, what's going on with this first term up here? And the y partial derivative of that first term is going to be 2 times e to the 2x. And there's no y's in the second part here. There's no y variables here. So that's going to be derivative of 0. And then we look at the middle term's x derivative, and that's going to be actually 2e to the 2x. So don't get all excited. Let me just expand this a little bit here. 2e to the 2x. Hope you're writing notes, because you can see everything on your paper if you're writing notes. Let's zoom back out again here. Now let's do the z derivative of the first component. There's no 2y e to the 2x. Its derivative is 0. But then the derivative of sine of z is cosine of z. So we're going to get here 2x cosine of z. And then we'll jump to the last component we see over here. And its x derivative is also 2x cosine of z. 2x cosine of z. Now you can see I'm starting to run out of space. Partly bad planning and partly the reality of when you've never done a problem, you don't know how it's going to fit out. So what we need to do next is figure out, well, what's going on with this last pair of partial derivatives. I'm going to put that down here. The z partial derivative of the middle term is actually 0, because there are no z's in the middle component. What's the y derivative of the last component? Well, it looks like there's a variable y there. Its derivative is going to be 1. Wait a second. Those aren't equal to each other. If any one of these pairs is not equal, then that means the conclusion is this is not a conservative vector field. F is not conservative. That also means there's no labor to find a potential function because it doesn't have one. So that's the therefore F is not conservative. Nothing else to check for. We're done.